Has it not been on the whole time?
Yeah.
So basically, it means that you can write something like this. You don't have. This is effectively what you have. You have a ref of L is effectively a pointer to something where you lay out the fields exactly as they're expected by the code that you're interacting with. And you have no choice but to deal with what the kernel asks of you. And it's represented as a pointer to an object plus an offset. And so that means that the garbage collected object can move, but the start of the object does not move. And so you can actually point to both something inside of a byte array and also outside of a byte array in the heap too. So it's kind of designed for being able to memory map things too as well. But this paper is not about that. It's about doing something similar for algebraic data types. So originally, Virgil only had classes and arrays and tuples. Can we turn this mic off? I think there's some, OK. And those are all on the heap. And so we need to point outside the heap, and we need to also do, I mean, obviously, people have done lots of encoding ADTs into classes. It doesn't really work. You really want ADTs in your language. And I finally concluded that the PLDI paper that I referenced said, you don't really need ADTs. You can encode them with classes. That was a lie. You want ADTs in your language. So this is the syntax that Virgil has. It's a lot like any ADT you might define in a functional language, just with more curly braces, because otherwise the C programmers will lose their minds. So we define a few cases here, and they have fields sometimes. You can desugar this into classes, of course, and that's like the first implementation that I had in my compiler. You basically just define a class inside for every one of the cases, and there's a superclass for the top. But that's inefficient because they're all on the heap, right? Every time you make a new value of one of these, it's an allocation. And so obviously, functional compilers don't necessarily represent them that way. You can represent them any way that you like, as long as you do the recursive comparison so that there's referential transparency. So some ADTs are actually hotter than others, like super hot, and you have like bazillions of them, and so you don't want to allocate them all on the heap. So this paper is all about some new annotations that are not semantically meaningful. So it doesn't change the program's behavior in any way to add an annotation like unboxed, but it just makes the compiler represent them differently so that they're more efficient. And so you can unbox all the cases by putting that annotation at the declaration of the ADT, or you can unbox a single case, in which case the compiler will make sure to unbox that one case, and all the rest of them it can kind of be boxed. So what does unboxing actually mean? It means that we're not going to allocate an object on the heap and have an indirection to it, but instead we're going to use multiple scalars or multiple words. And so I use the term scalar. It's a super overloaded word in PL literature, but basically think of it as a machine storage unit. You need at least to have one unit for the tags, so you need to be able to distinguish the tags. But what are the units themselves? I, again, stupidly chose, actually me and my student together stupidly chose scalars and to overload that. And it's effectively a register class. So a scalar can always go into a machine register. And so depending on your target, you may have some set of scalars. One target has some set of scalars. Another target has another set of scalars. It's the compiler's job to choose what that set is going to be used to implement the ADT. So it is not a word. It's not the same thing as a word, sorry. Some of them have opaque encoding. So ref is basically, this is a pointer where you do not get to see the representation of it. This is like a typical thing in any safe language. Then the other ones actually all have transparent encoding. So you can actually see the bits in one way or another. There's another way to slice this too, which is can you store a reference in there or not? So ref, obviously you can store a ref in there. R32 and R64, you can store a ref in there, but they're effectively kind of like a tag pointer. And the idea is that we're going to be able to use that to unify with primitive types so that you can pack two things into one word, and the tag will be distinguished by the runtime system. The other ones cannot store references, so you cannot mix them up. So you can do all the bit level tricks that you like with the other ones, and you can't confuse the garbage collector. So once you have source types, like classes and arrays, obviously they're going to map onto references. They can be opaque references. On the JVM, they can only be opaque references because there's no such thing as a tag pointer on the JVM. But on native targets, maybe we can use the other two. And then when you have integer types, they can map onto these B32s, and float types can map onto the F32s or F64s, and maybe also on the B32 or B64. So there's actually some choices. So every platform defines some set that you can use. So now you've got a problem. You have to basically pick which scalars are you going to use to implement this ADT, to represent them. So we call this the scalar assignment problem. You want to minimize the number of scalars, and this is, again, going to be subject to the target machine. So you can't unify like an integer and an object pointer on the JVM because there's no such thing, right? The other thing is you must be able to discriminate all the cases. So maybe there's not an explicit tag. It's easy to think of it as an explicit tag to discriminate the cases, but there may be other means by which you can discriminate them. So the question is, like, if we have this definition here, so there's four cases there, they have fields. So this was a 28-bit integer. This is a 32-bit integer. Here's another 28-bit integer. And you need to put a tag there. The tag has to be at least 2 bits. So it's effectively, they call them sum types for a reason. They have to add up to something. And so the easy way to do it is the greedy algorithm is you effectively start with the first case, you map the tag to some scalar, and then you map to each of the fields to some scalar, and then you have an intermediate solution, and then you go to the next case, and you do the same thing, and you try to reuse the scalars that you've already used for the previous solutions. So the greedy algorithm will just keep adding more scalars if they don't fit. So there's a kind of a unification going on. If you can unify with the previous scalar, you will do it. And so that's how you end up with tag pointers. So if you have a tagged representation like R32 available, and you have already ref, maybe you can reuse the ref as an R32. So this is the basic algorithm. There's also other ways to do this too. So for example, imagine that you had a ADT which is effectively defining either a string, which is exactly one string, so it's this, or maybe it's an array of strings. So those are both represented as objects on the heap. So the object on the heap actually has a tag, a runtime tag. So maybe you don't actually need to have an explicit tag for this ADT. You can use the tag in the indirection. So in this case, you can unify these two to be ref. And so you can represent this ADT, and you don't actually have to have any additional information. You don't even need tag pointers. So you can even do this representation on the JVM. But there's a wrinkle, which is the pesky null. Virgil has null. Strings can be null. And so you need to be able to distinguish between a case string of a null string and a case more of a null array of strings. So that's actually pretty easy to do. You can just consider them to be additional cases, and they can unify, and maybe you actually have a null, like 2 different null objects, and so you can tell whether you point to null object A or null object B, and then you still use ref to represent all of them. But that's not enough. You saw before that we had this case where we had 28-bit integer and a 32-bit integer. It's kind of a weird thing. Why would anybody do that? And the reason why is packing. And so that's the other part of this paper, which is packing ADTs. So we ended up with a pretty suboptimal solution where we had like 3 B32s for that one example. And there's subword quantities, actually, so we should be able to pack them together. And usually the tags are small because the tag is like the logarithm of the number of cases that you have. You only need a couple bits. So maybe we can pack them into the same word. There's also another really good reason to be able to pack ADTs, and that's that some ADTs actually don't come from our program, they come from the outside world. They come from some network packet description or something, again, in the same kind of vein as like the kernel demands that you put your data in this format. There are data formats that are similar. And here's one. This actually maybe isn't such a strict requirement because this came from the compiler, the Virgil compiler. But this is how some of the source information is represented in the backend. It's packed into a 32-bit word. I did this by hand, you know, late night, mad hacking and like bit mask everywhere. It's terrible, right? That code is like full of bugs, and I almost lost my mind debugging it. I wish I could have written this, because what really is going on is that a source entry is either an extended one, or it's some words, or it's a line column, and ADTs are the perfect thing to describe that. And if you notice, they're all subword things. This is 18 bits. I really squeezed them down. This is 18 bits. This is 11 and 8. And what the packing declaration gives you is the ability to lay out the bits exactly how you want them. So here we effectively use a binary literal. And then in the binary literal, of course, you can put 0 or 1. But you can also put a character. And the character is the name of the field. that you're using a bit from. So for example here, we're effectively encoding the tag as 1, 0, and then all the E's from this E field. And we just use the first character of the name so that, because that corresponds to a single bit. If you have two fields with the same name, it will complain at you, and you should rename them. And similarly, the interesting case obviously is the one at the bottom. We have two different fields. There are 11 bits in the first one, so we need to put those here. Unfortunate choice with L versus 0 and 1. But then you can put the C. And the underscores don't mean anything. Those are just separators. So the compiler will basically say, all right, you have given me a complete description of where you want to put the bits. You don't have to deal with it. I will do it for you. The issue is that you need to be able to actually discriminate them at runtime. So if you gave packings that were ambiguous, when you try to take the memory word and interpret it, which case am I doing when you're doing a pattern match, you should be able to decide. And so the compiler has an automatic algorithm, which is actually part of the paper that Jens and I wrote together in the Declarative Approach to Machine Code Tools. You basically build a decision tree, because you can take the concrete bits and you can take the set of patterns and you can recursively divide them. It's so easy that that was left as an exercise to the reader in the paper. But it's harder than just arranging the bits because we have pointer fields. So for example, maybe we want to make use of the fact that the runtime system can do tagged pointers. And so maybe we want to be able to pack primitives in with the case where there's a reference. So in this case, so maybe we're representing values in, for example, JavaScript. JavaScript engines do a lot of optimizations around small integers, which are 31-bit in size. And then effectively you have two cases, which is it's either a small integer, which is 31 bits, or it's an object. And then everything which is other a JavaScript value is some subclass of object. So what this ADT gives you is the ability to declare a packing where there's effectively a tag bit here. And the idea is that the other case, you don't say what its representation is. And if the compiler can find a solution to that, then you effectively get a tag pointer out of this. So then in your code, which you've already written to use values throughout the runtime system, you're just going to do pattern matches. You never have to deal with smize. So I worked on V8 for a long time. There's an endless array of code that does this. There are utilities, and you can do that in C++ using C++ arcane rules, but now you actually have a mechanism to do it in a nice language, and you just let the compiler do it for you. You may want to under-constrain the specification. We saw an under-constrained one there too, but maybe you don't want to write out every single bit. For example, it's kind of tedious to write those binary literals and make sure you got exactly 11 bits and they didn't overlap and things like that, and deal with tags. So there's some underspecified layouts where you effectively make the compiler do some of the work. So in this case, we've got a value, maybe there's an A case, 12 bits and 13 bits, but we actually don't care. We just want the compiler to put them in the same word. In that case, you can say packing X, Y. And that just means I want X and Y to be in the same word. If you want them to be in different words, maybe you can say A, comma B without the parentheses and just says separate these into two words. I don't care how you do it. I just want a packing where there's two words in the end. You can also use question mark. Any place where you have a binary literal basically says, I don't care about what that bit is. You can choose it. You can use it to represent. You could put, for example, tag bits in there. So the compiler effectively has a problem now to solve. And that turns out that that problem is NP-complete. So if you have a general graph, an undirected graph, you can encode it in JSON-C matrix into the bits here. I won't get into the construction of that. It's actually pretty straightforward, but the color is the question marks. So you just ask the compiler, I need to discriminate these things. These are the nodes actually that you want colors for, and it is going to pick them because the colors are the assignments to the question marks. There's one little detail there. You have to round it up to the next power of 2, so you have some cases that it's not allowed to use. And so this is actually fully general. So graph coloring, you're not going to have the compiler solve every packing problem for you. It's just not feasible. So what happens when that case occurs? So you wrote some packing declaration, and there's some ambiguity, and it just doesn't work. There's just no way to do it. And obviously, this should report some kind of an error. It's an NP-complete problem. How hard should it try before it finds a way to disambiguate? I don't know what the answer to that is. I think probably, we didn't actually solve that problem in the paper. It should probably be like, maybe it will try n squared. And then if it can't do it in n squared, it'll say, please, you give that to a sat solver and then come back to me. So I think that's probably what we'll do in the end, is that the compiler will complain if it can't do like the sort of specified n squared algorithm, and then you go off and ask the sat solver to do it for you. In practice, people aren't doing that crazy things with packings. They need that level of support. But this language is also great because it's bidirectional too. So I can write the packings that I want for my ADTs, but the compiler can also tell you what its packings are. So for example, I don't know what the target architecture is, but when I compile to x86-64 Linux, maybe I want to know what the runtime system does with pointers. So what is the representation of a pointer on that target? The compiler can just print it out for you. So this would be, for example, how are pointers represented in 64 bits? Well, actually, we're using a pretty small heap, so maybe they're all actually upper bits are 0, and then it's going to be all question marks. And it can also tell you they're all aligned, so the last 3 bits are 0. And so then you can write in your packing declaration that something that does not have zeros in its lower bits, and those are therefore discriminable. Similarly for nulls, nulls might be represented slightly differently too. So maybe we have some part of the heap, like maybe the lower, some part of the memory space is not actually part of the heap. So like maybe the low 1 megabyte of memory is not part of the heap. And so we can encode many different kinds of null things or smize in that range. And so they're going to be distinguishable from null pointers. IEEE 754 is the thing. So float has a specific representation, and that's what it looks like. So you can ask the compiler, hey, tell me what IEEE 754 is, and it'll tell you exactly how floats are laid out. And so you don't have to do the bit arithmetic yourself. So you might actually have to do a little bit of tinkering, because for a given target, maybe you have a tagging scheme in mind, and your ADT works on one target, but it doesn't work on another target. So you might have to relax it a little bit. So in our case here, where we're trying to do smize and refs, maybe we can't get 31 bits. And so maybe we back off a little bit and say, we only want 30 bits, and you get a question mark at the end. The compiler can use that. So we've implemented layouts, so that's stable and used in production as much as Virgil is a production language, but those are used in Wizard and other things. Unboxed actually works for manual annotations. It's respected when possible. There's really not good feedback. It basically, if unboxed doesn't work, because your ADT could be recursive, it could also be closed over. Closures have a special representation that where unboxing doesn't work. It may not tell you that it didn't unbox something. It'd be nice if it did. We're still using the simple greedy algorithm. It's not optimal. And the packing work is kind of a work in progress. So a lot of that is science fiction, what I said, but that's typical for research papers, right? And that's all I got. Thank you.
What's a smi?
Small integer.
I love the compiler problem. I wonder, is some of this like going to make it into WebAssembly one day?
Oh, that's a good question. So WebAssembly has like a second level type system in the component model. I'm not sure if you're aware of that. It is effectively like a data interchange language, and it has, I'm not sure if it has quite ADTs, but it has records and other things. So core WebAssembly has a low level type system, which is 32-bit and 64-bit machine level types. It might make sense to actually have it in the second level type system in this component model.
That would be cool. Okay.
Great. So with mutually recursive data types, for instance, you will have multiple ways you can, you might have multiple ways you can choose the unboxing. Have you, as a support for those things?
Right, so we thought about that too. So what you're referring to is basically you can have recursion through a specific field, and you may want to unbox that case but not that field. And so it may be that we should have the unbox annotation be allowed to be applied to fields, and that basically means box this field but not the entire chain, and you don't have to box the entire ADT. Yeah.
Okay, so in the age of LLMs, right? I wonder if one could, rethink, a programming language would be designed from scratch. What would be the ideal set of constructs that avoid all sorts of challenges that, the ones that the languages that do become popular face, right? Have you, tried this in sort of reflecting on Virgil's design? I have that liberty, right? I don't think the developers of Java or Rust have that liberty, but you would.
Yeah, I mean, that's a really open-ended and interesting question. I think I mostly thought about how LLMs might be beneficial if they could translate other code into Virgil. So not everybody knows how to write Virgil code, but you want to interface with that code. I haven't thought about what an LLM, I've tried to teach ChatGPT Virgil. It actually, I mean, it's read like all the publicly available stuff. It really wants to write Python syntax when I tell it. So it was able to write a mostly syntactically correct, like, pandemic simulator. I don't know why it wanted to write a pandemic simulator. I asked it write a program that simulates something, and it was like spread of disease. I have no idea why it did that, but it wrote, it wrote pretty decent Virgil code. And then after it reached this context window, it went back to Python. Maybe you can feed in the grammar to the LLM, and you can have it do magic PL stuff. That stuff is really exciting. I don't know where the future of PL and AI goes. I haven't really thought that through. Thanks for your question, though.